So good morning, class. You are welcome to today's lecture. I don't know why we don't have more students joining this class. Well, I want to assume that they are joining online. That is via YouTube. Okay, so today we continue with our S block elements. Last week, Friday, we looked at the group 1, that is the alkaline metals. So today we are going to look at the group 2 elements, which is usually known as the alkaline earth metals. Okay. So for our group 2 elements, we have our beryllium, magnesium, calcium, protium, barium, and radium. And it's always good for you to know the symbols also. So as I take the group 2 element, because it's also an S block element, I'm going to be, along the line, I'm going to be comparing it with some properties of our group 1 elements. So for the symbols, you already have them there, your beryllium up to your radium. For the electronic configuration, if you remember for the group 1, we saw that the valence electron had 1 electron in the valence shell. For your group 2, the valence electron usually have 2 electrons. So you see that also as we go down the group, the number of shells increases. That is why you have your beryllium, you have 2s, your neon, your magnesium, sorry, you have a 3s, up to your radium, which is now 7s. So what it shows that as we go down the group, the valence shell increases down the group. But despite the valence shell increasing down the group, they all have 2 electrons in their valence shell. And that is actually what leads, most times they have similar properties. We also look at the ionization energy. Ionization energy decreases down the group. This is also due to the increase in the valence shell, such that the valence electron is further away from the nucleus. So the ability for the valence electron to be lost is actually higher as we go down the group because of the distance, and also due to shielding effects. There's more shielding from the valence electron to the nucleus. So it's actually the same trend with your group 1 element. We also look at the melting point and the boiling point. If you look at the melting point and the boiling point, it actually decreases down the group. But if you look at the magnesium, you see that the magnesium deviated from the melting point and the boiling point. You see here that the magnesium, your beryllium is 1283 degrees, that is the melting point, while your magnesium is 650 and our calcium is now 850. So for your group 2 element, it's different from your group 1 element. The melting point do not vary regularly. And this is because of the crystal structure. They have different crystal structures. Your magnesium actually has van der Waals forces. So the bond in your magnesium is actually weaker. That is why you have it at 650. So it actually has to do with the way the metals adopt different crystal structures. That is why you have that variation or deviation, both in the melting point and the boiling point. And for the ionic radius, it follows the regular trend, where the ionic radius increases down the group because of course, the increase in the valence shell. Now, if you look at your group 2 element, you see that your radium is radioactive. And that is why we do not have values for your ionization energy, melting point, boiling point, and ionic radius. Unlike your group 1 element, where the only radioactive element there is your francium. And I told you that the half-life is 21 minutes. So in nature, we say that your francium does not exist because the half-life is just 21 minutes. But for your radium, your radium actually exists because it actually has a half-life of 1,600 years. And it's usually a radioactive metal that occurs from uranium. So we can actually find our radium in existence. So what are some of the characteristics of your group 2 elements? They are all metals. Your group 2 elements are all metals. If you remember for our group 1, I told you that, yes, your hydrogen is found in your group 1, but we don't say hydrogen is a metal because your hydrogen is a non-metal. So that is why we remove hydrogen from your group 1 element, despite that on the periodic table, you see it among the group 1 elements. So for your group 2 elements, they are all metals. As I said, they are known as alkaline metals, while your group 1 elements are known as alkaline metals. They are also good reducing agents. Of course, they are bases, so they are strong reducing agents. And they usually form ionic compounds, just like your group 1 element. Because for ionic compounds to be formed, the difference in electronegativity between the metal and the halogen has to be at least above 1.5 or 2. So here, because you have your metal, they are metals also. So combining with halogens, they usually form ionic compounds. So just like your group 1 element. They also form oxides. They also form hydroxides. And their oxide and hydroxide are basic, just like your group 1 elements. And when they react with acid, they liberate hydrogen. Now, among your group 2 elements, your beryllium behaves like lithium. So, and one thing I want you to note is that for all the group elements, like I'm taking you group 1 and group 2, somebody else is going to take you group, I think group 4 and 7. One thing you should note is that all the first elements are usually small. Their size is usually small with high charge. And this makes them to have their properties to be different from the other elements in the group. We saw this in group 1 for our lithium. We are also going to see it in our beryllium. Our beryllium is going to behave differently from the other metals. So like lithium in group 1, the exception to your common pattern in group 2 is your first element, your first member element, which is your beryllium. This also has to do with the size and the charge. So as I said, it has to do with the size and the charge, which makes it to have a high polarizing power. I think in our first lecture, I took time to explain the polarizing power. And it's because of this high polarizing power, due to the small size and the high charge, that makes these first elements to deviate in terms of their properties from the other elements. So its electrons are not well shielded from its nucleus, and because of the small ionic radius, so it has a small size and a high charge, so it has a high polarizing power, and this also makes this compound to be covalent than ionic. I also told you that your lithium compounds are more covalent than ionic. Now for your beryllium and its oxide are usually amphoteric. The other elements in your group 2 are basic. Your beryllium and the oxide, they are all amphoteric. What do you mean by amphoteric? I would have asked you to put it in the group chat. That means they behave both as basic and they have both basic and acidic properties. They can actually dissolve in both an acid and in a base. So they are amphoteric. And because of the small size too, your beryllium forms complexes more readily than the other group elements. Because it has a high charge, so it is the ability for it to form complexes with other metals is usually very high. Unlike the others, they don't usually, the ability for them to form complexes is not much. We are going to see formation of complexes more with the transition metals, and that is going to be our next lecture on Friday. You see that your transition metals, because of the presence of the partially filled d orbitals, they can form complexes. But this is not common with your group 1 and your group 2 elements. But because of the high charge in your beryllium, it can actually form complexes. It also dissolves in alkaline. As I said, it's amphoteric, so it can dissolve both in alkaline and your acidic medium, unlike the other group 2 elements. Also, your group 2 elements, like your group 1 element, are very reactive. So most times you don't find them free in nature. And when we say we don't find them free in nature, they can easily combine with your hydrogen, with your halogens, your sulfates, and your nitrates. So that is why we are also going to look at the oxo salt. So they don't occur freely in nature. So most times for you to get the free elements, you normally carry out electrolysis. And this is usually carried out with their fused chloride. We are not going to go into details into electrolysis, but just note that they are usually prepared from their fused chloride. A good example there is your magnesium chloride, because during electrolysis, once you collect the metal, the chlorine usually leave as a gas. That is why we normally use their fused chloride, so that the chlorine can actually leave the electrolytic cell. Now look at the reactions. As I said, just like your group 1 element, they form oxides, they form hydroxide, they also form halides. So the formation of your oxides, I already told you, just the reaction of the metal with oxygen. So here your group 2 metals, they can bond in air to form your oxides. But your beryllium is very, very unreactive. Your beryllium actually acts like aluminum. You see that in your group 3, your aluminum, okay, I don't know. I'm sure they did a diagonal relationship with you, with Professor Fashinal, where you see that your beryllium will have a diagonal relationship with your lithium. So because of that, you see that they actually have similar characteristics. That is why when we looked at group 1, your lithium was behaving more like group 2 because of the diagonal relationship your lithium has with your beryllium. So that is actually the reason. I'm sure you must have been taught diagonal relationship. So your beryllium is unreactive. And your beryllium is unreactive. I say it has similar characteristics with your aluminum because your beryllium has a film team covering it. So because of that, it's very difficult for your beryllium to react. It can only react above 600 degrees Celsius, but this will be in the powdered form. Of course, we know that as you increase the surface area, the reactivity will increase. So your beryllium among your group 2 does not react with oxygen, it's unreactive, but you also have the oxide. You also have your beryllium. So your beryllium and the oxide are usually unreactive because of the thin film that is formed on the outer layer. So, and for your group 2 metals, they form peroxide as we go down the group, just like your group 1. I told you that as we go down the group, because of polarizing power, that is the ability of the metal to distort the anion, then it reduces as we go down the group. So also that is why you form more of peroxide and the superoxides. The higher elements will distort more than the lower elements. So that is why higher elements will form more of your normal oxide, and as we go down, we form more of the peroxide and the superoxide. So your group 2 metals, because they are larger in size, you see that as you go down the group, we are forming more of peroxide and also the superoxide. Your barium peroxide is formed with ease and increased stability. So as we go down the group, you see that, as I said, you form more of peroxide. So your barium will form more of peroxide than the normal oxide. So we'll look at the oxide and the hydroxide of your group 2 elements. For the oxides, of course, I told you that formation of oxide can be when you react the metal with water or when you react the oxide with water. So reaction of your oxide with water will give you the hydroxide. So your group 2 elements, their oxide, when they react with water, will form hydroxide. But the exception is your beryllium oxide. Your beryllium oxide is insoluble in water. Your beryllium and your beryllium oxide is insoluble in water, and they don't also react with oxygen. But the others, they will react with water to form alkaline solutions. And as we go down the group, the alkalinity will increase, because as you go down the group, the element becomes more alkaline. They become more basic. But for your magnesium, the hydroxide is not prepared by a reaction of your magnesium oxide with water, because your magnesium oxide is not very soluble in water. Your magnesium also, like your beryllium, also has this thin covering around it. So your magnesium oxide is not very soluble in water. So for you to prepare your magnesium oxide, it's usually prepared by your magnesium chloride with sodium hydroxide. And this preparation of your magnesium hydroxide is very, very important, because your magnesium hydroxide is weakly basic. And because your magnesium hydroxide is weakly basic, that is why it's used as an antacid. That is usually a drug that you use in indigestion. That is what we call milk of magnesia. I'm sure most of you must have taken it when you had a constipation, or when you have your constipation. So when they say go and buy Mag or your milk of magnesia, that is your magnesium hydroxide. And it is used as a drug because it is weakly basic. You cannot use your calcium hydroxide because your calcium hydroxide is more basic than your magnesium hydroxide. So because of the weakly basic character of your magnesium hydroxide, that is why, and based on how it is prepared, that is why your magnesium hydroxide is used as an antacid. Your beryllium hydroxide is amphoteric. Your beryllium oxide, and your beryllium hydroxide, they are all amphoteric. But the magnesium, calcium, strontium, beryllium hydroxide are basic. But mind you, your magnesium hydroxide is weakly basic. The others are more basic than it. And that is why your magnesium hydroxide can be used as a drug. So as I said, basicity increases down the group. Another interesting hydroxide among your group 2 elements, aside your magnesium hydroxide, is your calcium and your barium hydroxide. They are called lime water. That is, your calcium hydroxide is called lime water, while your barium hydroxide is called baryta water. And we can actually use both of them in detecting our carbon dioxide in the lab. So in a situation where you are carrying out your qualitative analysis in the lab and you don't have your calcium hydroxide, you can actually use your barium hydroxide, which is your baryta water. So that is in detecting your carbon dioxide in the lab. And they're actually made by the reaction of their oxides with water. So when you have your calcium oxide, you dissolve it in water, that will give you your calcium hydroxide. When you have your barium oxide and you dissolve it in water, that will give you your barium hydroxide. Now, that is for the oxides and the hydroxides. Now, we'll look at the halides. The halides is also when you react the metal with the halogens. So that gives us the halides. And the most common ones among your group 2 halides is the chlorides. The chlorides are the most common halides, although we also have the fluorides, the bromides, and the iodides. But the most common chlorides that we are going to look at is usually the chlorides. And the chlorides, they are all soluble in water because they are ionic. They form ionic compounds. So example of your halides, if you have your sodium chloride, that is a halide. So you have your sodium and your chlorine, that will form your sodium chloride. And as I said, because the difference in electronegativity between your metal and your halogen is much, so that is why they are able to form ionic compounds. So, and because they form ionic compounds, that we say that they are all soluble in water, because like will dissolve like. Your sodium chloride is polar, your water is polar. So that is why they will be soluble in water. And again, they form hydrates. They form hydrates. Good example is your calcium chloride. What it means is that they have water of crystallization. Most of your group 2 elements have water of crystallization. And we are going to see some of the importance of these elements that have water of crystallization, like your calcium chloride, your barium sulfate. We are going to see how many water of crystallizations they have, and most of them have good medicinal properties. Again, among your group 2 halides, your beryllium chloride exhibits 2 types of structure. This in the solid form. You have the linear, and also you have the polymeric type. So your beryllium chloride exhibits 2 types of structure in the solid form. We have your beryllium halide, your beryllium halide, especially the chloride, exhibit 2 types of structure, the linear and the polymeric structure. This is the linear structure, which you have here on your slide. This is the linear structure, and it has a bond length of 180 degrees, and the hybridization is sp hybridized. Now, for the polymeric, this is actually the polymeric structure. For the polymeric structure, it has 4 bonds. We have 2 covalent and 2 coordinate bonds for the polymeric form. And the structure, actually, each of the bonds exhibits sp3 hybridization, unlike the linear structure, which exhibits sp hybridization. It's 180 degrees, the bond. But for this is actually sp3 hybridized. And as I said, it has 2 covalent and 2 dative bonds. Now, your beryllium chloride is covalent in character. It's not ionic. Because if you look at the difference in electronegativity between your beryllium and chlorine, it's not much. And also because of the polarizing power of your beryllium. So your beryllium chloride is covalent in character. So aside your beryllium chloride, the other chlorides, their ionic character increases down the group, because as I said, as we go down the group, basic nature increases, and of course the ionic character increases. As I said, most of these compounds actually have good properties. Example is your calcium chloride. Your calcium chloride is deliquescent. That means it can absorb water from the atmosphere, and that is why we use it as a drying agent. Your calcium chloride. Your anhydrous calcium chloride is deliquescent, and you can actually use it as a drying agent. So we've looked at the oxides, formation of the oxides, the hydroxides. We just finished the halides. So we also looked at the oxosalts, and we are going to look at the carbonates and the hydrogen carbonates. We looked at the group 1 carbonates and their hydrogen carbonate. They are all solids. Also, your group 2 carbonates are solids, but they are slightly soluble in water. They are solids, but they are also soluble in water. But your group 1 carbonates are more soluble than your group 2 carbonates. And the reason is that your group 1 elements are more basic than your group 2 elements. So that is why also their carbonates of your group 1 carbonate are more soluble in water than your group 2 carbonate. So as we go across the period, what happens is that basicity increases, acidity increases. So we are going from, so the basicity is actually reducing. And as basicity reduces, then solubility will also reduce. So that is why your group 2 carbonates are slightly soluble in water. Solubility also decreases down the group. Now, for the oxosalts, your carbonates, just like your group 1, when it's Heated, it will give you the oxide and the CO2. So on heating your group 2 carbonate, it will give you the corresponding oxide and the carbon dioxide. And also the ease of decomposition decreases down the group. If we remember also, when we looked at our group 1, you see that our group 1, when we heat the carbonate, it will give us the oxide and also your carbon dioxide. It is only the hydrogen carbonate that will give us the sodium carbonate, CO2, and the water. Now, unlike your group 1 metals, which possesses sodium solid hydrogen carbonate, the group 2 hydrogen carbonate only exists in solution. And this is why when I was teaching group 1 carbonate, you saw that your lithium carbonate, your lithium hydrogen carbonate actually exists in solution. That is the only hydrogen carbonate among your group 1 element that is not a solid. You see that it's behaving like your group 2 element. So your group 2 hydrogen carbonate all exist in a solution. But your group 1 hydrogen carbonate, they are all solid except your lithium hydrogen carbonate. Please always note these deviations. So we look at the sulfates. I'm going to ask you a question at the end of this lecture. So please make sure you pay attention. So we'll also look at the sulfates. All your group 2 metals, they form sulfates. So we have our beryllium sulfate, we have our magnesium sulfate, we have our calcium sulfate, we have our strontium sulfate, and we have our barium sulfates. Now, for the sulfates, the solubility of the sulfate in water decreases down the group. The solubility of the sulfate decreases down the group. And this is because of the small size of your beryllium and your magnesium. You see that your beryllium and your magnesium will be more soluble. As we go down, your calcium, your strontium, and your barium will be insoluble in water. So the solubility has to do with the smaller ion of your beryllium and your magnesium. So we say that the solubility is due to the high enthalpy of solvation of the small beryllium and magnesium ions. So it's easy for them to actually go into solution than your calcium, strontium, and your barium. And also, because of this, we are going to see, because of the solubility trend in your sulfate, we are going to see how these compounds are used medically. So your beryllium sulfate and your magnesium sulfate are soluble. They are very soluble in water. Your calcium sulfate is thoroughly soluble in water because as we go down, solubility decreases. Your strontium and your barium sulfate are insoluble in water. So now, as I told you, the sulfates of your beryllium, your magnesium, your calcium are found as hydrated crystals. So they have water of crystallization. Your beryllium, your magnesium, and your calcium, they all have water of crystallization. We saw that our calcium had six molecules of water of crystallization from the other slide. Your beryllium has 4, while your magnesium has 7. Your calcium has 2. Your calcium has 2 water of crystallization. Your calcium sulfate. It's actually your calcium hydroxide that had 6 molecules of water. Your calcium sulfate has 2 molecules of water. So we say that they are usually hydrated. That is in terms of solubility. Now, what about stability? The stability of your sulfate actually depends on the basicity. And you will agree with me that as we go down the group, basicity increases. So the more basic, the more stable. You see that your beryllium sulfate can decompose at 500 degrees Celsius, while your strontium sulfate will decompose at 1,374 degrees Celsius. So stability of your sulfate depends on basicity. So as we go down the group, basicity increases and stability increases. So now let's look at some uses of your group 2 sulfates. Because of the solubility of your group 2 sulfate, most of them have good medicinal use. I'll repeat that again. Because of the solubility, because as you go down the groups, solubility decreases. You see that your beryllium and your magnesium are more soluble. And that is why your magnesium sulfate is used as a mild laxative. That is your Epsom salt, because it's very soluble in water. Your calcium sulfate, as I told you, is thoroughly soluble in water, and it's known as your gypsum salt. And because it's thoroughly soluble in water, that is why it's used in your what you call your POP, your plaster of Paris. So you can use it in the treatment of broken bone. Also, that is, in for the making of the sealing, that is your plaster of Paris. That is actually what they use, your calcium sulfate. So it's because of the solubility in water, such that when it's being applied, it's fairly soluble, but with time, it solidifies. If it's already very soluble in water, it cannot be used as your plaster of Paris. And if it's already solid, then it cannot be used. But because it is thoroughly soluble, it can then be used as your plaster of Paris in the treatment of broken bone. Your barium sulfate is the last among the group. You saw that we said that your barium sulfate is your barium sulfate and your strontium sulfate is insoluble in water. So because of this insolubility of your barium sulfate, it's actually used in diagnosing stomach ulcers. Because most times when you take it, it actually forms like an opaque solid on the stomach, because the stomach is very, very soft. It's difficult to take the X-ray of the stomach. So most times your barium sulfate is used such that if you ingest it, it will form something like an opaque structure. It will form opaque structure, or it will form like an opaque compound on the stomach, so that it's a little bit hard, so that the X-ray picture of the stomach can actually be obtained. So it provides like something like a shadow on the stomach, so that the X-ray of the stomach can be obtained. So it's because your barium sulfate is insoluble in water. That is why you can actually use it in diagnosing stomach ulcers. So these are some of the uses of your group 2 sulfate. And as I was teaching, we saw that along the line, we also saw some of the uses of your other group 2 elements, like your calcium chloride. I told you you can actually use it as a drying agent because it's a deliquescent. So these are some of the uses of your group 2 sulfate based on the solubility of your group 2 sulfates. So any question? So I said I was going to ask you a question. So the question I want to ask you, I want you to put it in the group chat. Why is beryllium and its compounds? Why is it that beryllium and its compounds don't react with water and they don't react with air? Beryllium and its compounds, they don't react with oxygen, they don't react with air, water, they don't dissolve in water. Why? I want you to put it on the group chat. I can't see your answers. Hello, can you hear me? If you can hear me, put it on the group chat. Okay, I asked the question. You answer that you can hear me, but I asked the question. I can't see any answer on the group chat. I said, why is beryllium and its compounds, why is it that they don't react with water? They don't react with air, they don't react with water. I'm waiting for your answers. This one said they are not ionic in nature. This one said because of his high polarizing power. So this one says protective oxide layer and high. Yes, I told you that your beryllium and the oxide has a protective layer. So because of that, it does not react. It does not react with air. It does not react with water because of the protective layer. It's just like your aluminum. Your aluminum does not react with water because it has a protective layer. So I'll ask you another question. Give me one similarity between most of you are not answering the question. So what is the similarity between your lithium hydrogen carbonate and your group 2 hydrogen carbonate? Why do we say they are similar? Your lithium hydrogen carbonate and your group 2 carbonate. Why do we say they are similar? Your lithium hydrogen carbonate and your group 2 hydrogen carbonates. Only 2 people, 3. They occur as solution. They are soluble in water. Okay. They are not solid. Okay. What are the two forms of your beryllium chloride in the solid state? What are the two forms that I told you that your beryllium chloride can exhibit in the solid state? What are the two forms? Only how many people have answered? 3 people. Linear and polymeric. Okay. Okay. So I'll ask you one final question, and I want you to think about it properly. We just looked at the group 2 sulfates, and we saw that your group 2 sulfates, they have a lot of medical applications. These medical applications, what is the basis for the use of this group 2 sulfates in medical practice? What is the basis for their use? Why would we use them? So the basis of their use is based on what? Which of the properties? Is it their acidic property? Is it their solubility? Is it their stability? What is the basis of the use of this group 2 sulfates? Is it based on their basicity, alkalinity, stability, solubility? What is it based on that we use them in medical field? Your sulfates, your group 2 sulfates, the sulfates. That was our last topic. Somebody is saying some is saying their basicity, some are saying their insolubility. So as I told you, it is actually based on their solubility. That is why they are used in different fields in medicine. It's based on their solubility. That is why they are used. Okay. We've tried to just go through what our lecture this morning. So that will give you a better understanding of our lecture. So any question? So any question? Question?
Yes, ma.
Okay.
Yes, ma. Sorry, ma. You mentioned something about group 1 elements, about francium having being radioactive, and then you said something like that is not really an element because of it breaks down. Can you explain more on that, ma?
I said your group where your francium is radioactive. Why I said that in nature we said that your francium does not exist because of the half-life. The half-life of your francium is 21 minutes. You agree with me that when I started this lecture, if your francium was produced by radioactivity, you agree with me that from the beginning of this lecture till now that we have ended it, your francium has disappeared from the earth because the half-life is just 21 minutes. So that is why we say in nature your francium does not exist because of the half-life. I told you that your radium has a half-life of 1,600 years. So it's because of the time it takes for it to disappear from the earth. That is why we say that your francium in nature does not exist because it will take only 21 minutes and it's off the earth. Does that answer your question?
Thank you, ma'am.
Okay.
Yes, ma'am, it does.
Okay. I said I'll give you the slide, but the lecture is already posted now. You have it on YouTube. So what do you need the slides for? Huh? The lecture is recorded, and at the end, I normally see it on your platform. And the lecture comes with the once you open the lecture, once you open the YouTube link, you'll see the slide there. So I don't really think you need the slide again. You can always see the slide from the recorded from the recording. Sorry. Any other question? Okay. So that's the end. So if no other question, I think that's the end of. That should be the end. So I'll see you on Friday. I'll see you on Friday, and on Friday we are going to look at okay, I think we have one more slide. Okay, uses of some other group 2 elements. So let's just complete this. Beryllium is used in nuclear reactors as a moderator. Magnesium is used in metal alloys. You can use it in making alloy for aircraft because it's light. Your magnesium metal is very, very light. And that is why you can use it in aircraft. Metals that are light are usually used in aircraft. Calcium is useful in the body for healthy bones. You see, most times when you have a bone problem, they give you calcium to drink. So calcium is used for healthy bones. Your strontium is used in radiochemistry. Your barium, I've already told you, your barium forms alloys with other metals such as lead and calcium, and is used as your barium meal. Your barium meal is actually used, as I told you, that is when we use it in stomach ulcers. So we call it your barium, that is your barium sulfate. It's used as a barium meal in medicine. So you ingest it and it forms an opaque around your stomach. With that, you can then be able to take the x-ray of your stomach. So these are some of the other uses of your group 2 elements. I think that is the end of our lecture. So I think I'll see you on Friday, and we'll start with, I think, transition elements. Then by next week, the other lecturer will come in.
Sorry, ma'am.
Okay.
Hello, ma'am.
Yeah.
I just wanted to confirm. You said group 2 elements are used in medical applications. Is it because of their solubility or insolubility? Sorry, ma'am.
I said group 2 sulfates. It was the
Okay.
sulfates we looked at. We looked at our beryllium sulfates. We said that beryllium sulfate and magnesium sulfate are soluble. Calcium sulfate is spirally soluble. Your strontium and your barium sulfate are insoluble. And we'll look at their properties. Your magnesium sulfate, because it's soluble in water, is used as a mild laxative. So it has to do with their solubility. Your calcium sulfate is spirally soluble, so it's used as your plaster of Paris. Your barium sulfate is insoluble. That is why you can ingest it. It will not react with your body. So it's insoluble so that you can use it in diagnosing stomach ulcers. So it's because of their solubility trend. That is why your group 2 sulfate are used in medicine. It's based on their solubility trend. Does that answer your question?
Yes, ma'am. Thank you so much, ma'am.
Okay, okay. So any other question before we call it a day? Okay. So I'll see you on Friday, 8 o'clock. Thank you.